So in the last data set, we ran our sample data through DSeq and asked DSeq for pairs of conditions to evaluate the significance of the genes. So in this table that DSeq produces, we've asked DSeq to run the negative binomial-based test to test the null hypothesis that the distribution of each gene is the same in the 3-day condition and in the 18-week condition. Or sorry, in the 2-day condition and the 18-week condition. So when we ask DSeq to run this test, it gives us a table which gives us the results for each test. And here we're just sorting the table by p-value with the smallest p-value up top. So this is the most significant gene. So this was the gene that was most different by the negative binomial test between day 2 and week 20 with a p-value of 1.4 times 10 to the minus 14th. This is the gene that's the second most difference with a p-value of 1.3 times 10 to the minus 12, and so on and so forth. But when we report these results, we don't actually use this column, which are the p-values coming from the negative binomial test. We use this column called p-adjust. And this p-adjust is going to turn out to be Benjamini and Hosberg false discovery rate correction for multiple hypothesis testing. So actually, you'll often see in the literature some threshold based on this adjusted p-value, and again, this will often be called the Benjamini and Hosberg adjusted p-value, and some threshold will be chosen like 5 or 10%. Here we're using 10%. So we might ask how many genes were significant at a 10% Benjamini and Hosberg FDR threshold, and we do that in R by asking. We say to R, show us the all of the genes that for which this column is less than 0.1. Right. So when you do this Boolean selection in R, anytime this is true in R, you get a 1, and anytime it's false, you get a 0. So every time this is true, you get a 1. So there's 136 cases in which our $ p-adjust is less than 0.01. So we say that there's 136 genes that are significant at a 10% false discovery rate. But why do we have to do this? Why can't we use this p-value column? What's happening? Like, why do we have to use this p-adjust? And notice the p-adjust numbers, p-adjust p-values are bigger. We've lost power. They're less significant than the unadjusted p-values. So what's happening here? So to begin to answer this question, we can do a very simple simulation in R. So one thing that I've said to you over and over again over the course of the semester that we've really emphasized is that when you have a null hypothesis that's always true, and you run a statistical test such as DSeq with its negative binomial distribution or a simple t-test, when you run a statistical test over and over again, when the null hypothesis is true, the resulting distribution of p-values is uniform. So we can turn this around and use this uniform distribution to simulate an experiment in which we have 20,000 genes that have been run through a pipeline like DSeq. So we can do this very simply in R by just using RUn of 20,000. Right? So this RUn of 20,000 simulates an experiment, a genomics experiment, say an RNA-seq experiment on 20,000 human genes, in which we're comparing two conditions, but the null hypothesis is always true. So there's no difference between the two conditions. Right? And so of course these p-values are uniformly distributed. So on this experiment, it's not correct to use a simple threshold of significance of 0.05. It's not correct to use the simple p-value as your threshold of significance, because just by the definition of the uniform distribution, just by the definition of a p-value, about 5% of the time we expect to see a p-value of less than 0.05, even if the null hypothesis is true. Right? That's what a p-value is. It says if the data were random, how often would you incorrectly think that there was a difference when there really wasn't a difference? And we can see that happens just about 5% of the time, which by the law of large numbers, since 20,000 is a fairly large number, the number of genes that we're going to get that's close to 1,000 is going to be, or the number of genes that we're going to get that's less than 0.05 is going to be pretty close to 1,000. Right? So again, we can simulate this in R very quickly, right? So we can start a session in R, and we can just say, okay, here are my p-values from some experiment. Here's 20,000 p-values. Null hypothesis is always true for 20,000 genes. Here is the distribution of p-values. It's going to be close to uniform, and I can ask how many of these 20,000 genes is less than a simple threshold of 0.05, and it's always going to be fairly close to 1,000. So clearly this simple threshold of 0.05 isn't appropriate, and we're going to talk about two thresholds that are appropriate, more appropriate for genomics, where you have these multiple hypotheses that you're running. So the simplest of these to understand is called Bonferroni correction. And Bonferroni correction says, okay, well, instead of using a threshold of 0.05, just divide the threshold that you're using by 20,000. Okay, so here we simulate our 20,000 genes at 0.05 divided by 20,000. If you want there to be only a 5% chance of any false positives across the 20,000 genes, then set your threshold to 0.05 divided by 20,000. So we say the threshold is 0.05 divided by n, where n is the number of hypotheses that you're running. Right? And so when we do this, there are no p-values that are going to be below this Bonferroni corrected threshold of 0.05, right? So when we go back to our R window, all we have to do is divide this by 20,000, and we now have an appropriate threshold where we're not reporting any false positives. So in R, if I have a data set where I have these 20,000 simulated p-values, and I have my threshold of 0.05 divided by 20,000, so this is one way to express the Bonferroni correction, is to take 0.05 and divide it by 20,000. Another way is to, so here I've changed the threshold, but I've kept the p-values the same. Another way to do this adjustment is to adjust the p-values directly. So I can do p.adjust of these p-values, and I can use the method, set the method equal to Bonferroni, except it might be capital B. Nope, it's lowercase b, I had that right. So I say p.adjust p-values method equals Bonferroni, right? And so here, so in this case, I've adjusted the threshold by dividing by 20,000, but by using p.adjust, I don't have to type in the number 20,000. R knows there's 20,000 p-values here. It multiplies each one of the p-values by 20,000, and then if that number is greater than 1, it just caps it at 1. So you can either change the threshold, or you can use p.adjust, and R will change the p-values for you. And this is equivalent to what DSeq is doing, except using Benjamini and Hochberg correction, which we'll look at in the next slide. So you will often see it argued in the bioinformatics literature that Bonferroni correction is considered too conservative, or sometimes can be considered too conservative for genomics experiments. You will see it argued sometimes that this threshold of p divided by n is too harsh, right? With the small sample sizes, you just won't ever be able to reach it. So there's a less conservative alternative that is often used in the literature. This is the Benjamini and Hochberg false discovery rate. This is what DSeq is giving you in its p-adjust column in that spreadsheet that we looked at. So at a 5% false discovery rate, you expect 5% of the hits to be false positives, right? So this is less conservative for than for Bonferroni correction, where there's a 5% chance that any of the hits are false positives, right? So if I give you a list of 100 genes that have a 5% false discovery rate, I'm saying I actually think that 5 of these are going to be false positives, right? So if my statistics are working, 95 of these will be true positives under Benjamini and Hochberg false discovery rate correction, but 5% will be false positives. And that is less conservative than saying that there's a 5% chance that you have any hits that are false positives. So this is a little bit trickier to calculate, but not that tricky. I'm going to give you something that's very close to what you'll get by typing p.adjust in R. It's not exactly how R does it, and I'll explain a little bit about the differences, but this will give you a flavor of what R does. So to get the Benjamini and Hochberg false discovery rate, first or to adjust the p-values, first you rank all the p-values, smallest first, right? So here we have a bunch of p-values, and the smallest p-value is here. And the rank of each p-value, let's call that k. So this column here is going to be k, right? So k equals 1, 2, 3, 4, and 5. So then we calculate for each column n. N is the number of tests that you've run, so that would be 20,000 in our simulated data set. P is the p-value of each rank, right? So the p-value here would be rank 1, the p-value here would be rank 2, and so forth and so on. And k is the rank. It's the hit number. Okay, and then you start at the top of the list and you go down and you calculate n times p divided by k. And if that's greater than some threshold, like 0.1, you would say that you have a hit at 10% false discovery rate. Now, one difference in the way that R does the correction in this formula, it has to do with sometimes this number can go up, right? Because k is going up. So like here you can see that that this p-value of 0.66 is lower than this p-value of 0.60. So R actually will back propagate that 0.66 up. And that's what you get when you type p.adjust in R with the method equals bh, and we'll take a look at that in a second. So here we just have some simulated data, right? Here's our 20,000 simulated data sets or genes where the null hypothesis is always true. So our 20,000 simulated genes where the null hypothesis is always true. And I just go and I correct the, notice I have a sort here, right? So there's a lot happening in this one line. Sort the 20,000 p-values. So the most significant ones up top, and then just calculate this n times p divided by k, right? So I just go from 1 to 20,000, and this is n times p divided by the rank. So it probably would make the code a little bit clearer if this was k, but here k equals I. And then pop open a data frame, and what we can see is that even without doing this R trick of taking the larger number and propagating up, none of these numbers are below 0.1, and so our false discovery rate correction worked here. The null hypothesis was always true, and we didn't report any significant genes. And again, if we go back to the R level, right? If these are my p-values, this is my histogram of p-values, right? So I can now adjust the p-values by two methods. One is the Benjamini-Hochberg method, where we're essentially just multiplying each p-value by 20,000 and then capping it at 1. And now we have this new method called Benjamini-Hochberg. And you can see this is a less conservative method, right? These numbers are not quite as large as 1 because this n times p divided by k is a less stringent thing to do than simply multiplying by 20,000. So again, we now have a good understanding of what DSeq is telling us and why we use this column, why we use the adjusted p-values, because if it's naive to only use the p-values here, because even if the null hypothesis was always true at a simple threshold of 0.05, you would still see hits that are significantly different. And the way that you will usually implement this in R is, rather than changing the threshold, is use this magic p.adjust command, and then the p-values will be adjusted. And once the p-values are adjusted for multiple hypothesis testing, you can do things like scan for a particular threshold. So here I can say, what's the threshold of the adjusted p-values that are less than 0.05? And this would be the number of significant hits. And in this case, there are no significant hits because the null hypothesis is always true under the data that I've simulated.